Okay. It is 1 o'clock on the nose. Do we want to wait a couple minutes or should we continue? Come on in. Great. Um,
It's up to you, Travis. We can wait a minute or two, or
sure. Let's wait 2 minutes.
that's good.
At Here at work, we have shortened our meetings to start at five after and begin at or end at 5:02 to allow folks to transfer themselves in between meetings and use facilities and whatnot. So my brain is automatically wired now to give just a little bit of a buffer to folks. So, but we have lots to talk about today. Oh, my camera. Okay. Well, let's get started. Today is February 17th, 2026. We are presenting yet another AGN Science Interest Group Vision Series presentation. Hi, I'm Travis Fisher as part of the AGN SIG leadership. And we're here to listen to Dr. Santiago Garcia-Burillo talking about the ALMA view of the gas cycle in nearby AGN. So before we jump into that, we have just a few couple announcements to discuss with everybody. The first one is that we're beginning to prepare for Astro 2030. So we had discussed this at our AAS Splinter session and how we're getting ready for the next decadal survey. And we met recently with the Cosmic Origins Program Analysis Group, or the COPAG, executive committee. And so what this is it's a forum that helps advise NASA's astrophysics division. And what they're trying to do right now is finalize the questions that are going to be proposed to the community to hopefully get information for the next decadal survey. So some of the questions that they floated to us that are examples, not official in any way, are is there anything from Astro 2020 that we are still needing to work on for Astro 2030? What kind of instrumentation, what kind of like technology do we need to answer those questions? And then what kind of missions would we need to be putting together to support the answering of those types of questions? So what they're looking for, though, are more valuable, broad questions that we should be thinking about to prepare for the decadal survey. And so that's what we're here to ask you for help on, is to use this QR code. This is a simple one question questionnaire that you can just give your input on a potential interesting question that we should be thinking about. This is a very short turnover. We're asking you to take a look at this today through Thursday this week because we need to deliver answers to the leadership by February 25th. So we would take whatever is provided by the community, collate that, and try to digest it for them to give them a condensed version of some really interesting questions. So please take a look at that and help us define the questions that will guide the next decadal survey. Secondly, we'd also wanted to inform people about our dissertation jamboree. We were discussing this previously at our last Spotlight series, and what we're looking to do is create a week-long dissertation set of talks to highlight recent PhD graduates. So this is really helpful, we think, for folks that are trying to showcase their work, try to provide some sort of literature for them when they're citing themselves for the job market. These talks are recorded typically, so this gives folks the somewhere they can point to say, "Here's me speaking." You can get a feel for who I am. You can get a feel for what I'm talking about, and sort of work on your high visibility talks. So we're looking to provide the resources for 2 to 3 speakers per day for over a week. And your talks that you would be providing are similar to what we see at the AAS, at the American Astronomical Society, where a dissertation style talk is approximately 20 minutes, 15 minutes plus 5 for questions. So if you're interested in partaking in this, maybe you've graduated recently, you're graduating soon, please check out this QR code, a separate QR code, and submit any interest by March 13th, which is a little less than a month, lots of time. So we can remind again at the AGN Astro Coffee that we'll be having at the beginning of March. But we need your talks. We want to highlight the next generation of AGN researchers. So please partake if you are graduating anytime in the near or previous and near future. Great. So with that, I'm going to stop sharing. I'm going to figure it out how to do that. And oh man, I'm sorry. I don't know how to drop down. So I want to stop sharing here. I'm going to figure it out. This one. Oh, stop sharing. I found it. Sorry. Okay, so we'll stop sharing and I'll pass the microphone over to Santi and so that he can present his work on the ALMA view again of the gas cycle in nearby AGN. Santi, take it away. Thank you very much for joining us today.
Okay, thank you very much, Travis. This is a pleasure to give this talk to this audience. So the ALMA view of the gas cycle in nearby AGNs. I'm gonna be very ALMA biased because I'm an ALMA person. So the bulk of the gas which is giving rise to nuclear activity lies originally on galactic scales, which is far away from the accretion disk. So in this talk, I will try to review very briefly the reasons why high spatial resolution studies of AGN are needed to understand the processes that encompass 3 orders of magnitude in spatial scales from the host galaxy to the sphere of influence of the black hole. And these observations are required to study AGN fueling processes, to detect and spatially resolve AGN tori and the associated dusty molecular outflows, and also to reveal whether AGN feedback is imprinted on the distribution and the kinematics of molecular gas, but also on star formation. Of the fueling of supermassive black holes has to tackle with a severe angular momentum problem. And this is because the specific angular momentum radial profile of typically rotating disks increases with radius. That implies that material needs to lose 3 orders of magnitude of its angular momentum to reach the region of the accretion disk from the galactic scales, typically kiloparsec scales, down to the accretion disk itself. Inflow processes on extragalactic scales are connected to environment. Observations and numerical simulations illustrate the role of major and minor mergers, chaotic accretion, including flows, but on galactic scales, several secular processes are able to drain the angular momentum from the galactic scales down to the sphere of influence of the black hole. This includes accretion of stars lying in the lost cone. This is mainly found in nuclear scale gas poor galaxies, but in gas-rich galaxies, most of the component that's going to fuel the AGN is the gas itself. And this is because of the combination of several mechanisms, including large-scale spirals, bars, acting on the gas, but also smaller scale stellar distribution or perturbations like nuclear bars, nuclear spirals, and lopsided instabilities that act on the gas and are able to drain its angular momentum. How do we expect that this is going to work in gas-rich these galaxies? Well, we know that due to its dissipative nature, gas tends to follow orbits that are tilted relative to the back axis, and this will end up delineating spirals at different radii. And the gravity torques exerted by the bar on these gas distributions change signs depending on the location inside radius, and depending on the location relative to the resonances of the bar. These torques are positive of cycle rotation out to the outer limit resonance of the bar. The torques are negative in cycle rotation down to the ILR resonance. And what happens inside the ILR is tricky. It depends whether the gas is lying outside the sphere of influence of the black hole or inside the sphere of influence of the black hole. That depends basically on where the gas is located. And of course, this depends also on how massive the supermassive black hole is. If the gas is lying outside the sphere of influence, then it will delineate leading spirals, and the torques are going to be positive, and as gas is going to pile up in the ILR ring. So the ILR acts as a gravity torque barrier. If gas is able to make it close to the sphere of influence of the black hole, and that depends also on the mass of the supermassive black hole, it will delineate trillion nuclear spirals. And along these spirals, torques are negative. So gas is going to fuel the AGN. So that's the on analytical grounds the expectation, but do we see any evidence that this kind of perturbation exists in real galaxies? And the answer is yes. There is mounting evidence of the existence of nuclear spirals, trillion nuclear spirals in some these galaxies, and that's thanks to ALMA observations of these galaxies, but also evidence of lopsided instabilities, what we call M=1 instabilities. And both instabilities are able to drain angular momentum very efficiently down to the sphere of influence of the black hole. These are two cases that clearly illustrate the efficiency of these instabilities to drain angular momentum. Of course, you need high spatial resolution observations for the gas, because to get the gravity torque budget right, you need to measure accurately the gas phase, the phase shift between the gas response to the stellar potential. Do we see any evidence of these instabilities in simulations? In fact, state-of-the-art numerical simulations, either including AGN feedback or not including AGN feedback, show the presence of this type of instabilities, both nuclear spirals and lopsided instabilities. And the gravity torques of these key actors are indeed able to drain angular momentum of the gas down to the sphere of influence of the black hole, down to the tori. AGN tori represent one of the very last steps in the let's say in the trip of the gas on its way to the black hole. So understanding the nature of these AGN tori is central to understanding the gas cycle in AGNs. Unified theories of AGN interpret the wide variety of properties of AGNs as due to the obscuration of AGN radiation by the presence of a dusty molecular passes scale torus. This compact disk will be responsible of absorbing the UV and optical radiation and reprocess this into the infrared, and they also would contribute to X-ray reflection and absorption. Anyway, in these unified theories of AGN that were initially put forward by Antonucci and Miller in their seminal paper, the torus, this compact disk of dust and molecular gas material, is the key ingredient. Now the question is, do we have any direct observational evidence that these compact disks exist, and what are their properties? Facilities like the VLTI and ALMA have been instrumental in showing the existence of these compact disks. In particular, ALMA can image the dusty molecular tori in nearby AGNs, reaching this kind of spatial resolutions, a few tens of parsecs, using several frequency bands. And this is because of the large number of antennas and associated baselines. So ALMA is able to produce high fidelity images of these tori if they exist. In contrast to infrared observations, ALMA is sensitive to the coal dust gas component of these compact disks and probe a wide range of physical densities and kinetic temperatures. And this cold phase of dust and gas represents the bulk of the mass in these compact disks. ALMA can also image whether these tori are connected or isolated relative to the galaxy host, whether they are connected through inflowing structures or outflowing structures. So, a quick summary of ALMA results. The first is, of course, NGC 1068. ALMA was able to obtain the first image of the submillimeter counterpart of the molecular dusty torus in the Cipher-2 galaxy NGC 1068. In particular, ALMA emits a 25 parsec size disk, molecular disk. So first surprise is the size. It's not parsec scale. It's a few tens of parsecs. And the torus is also, maybe also another surprise, is quite perturbed dynamically speaking. We see rotation, but we see also outflow motions superposed to rotation. And we interpret this outflow motions, non-circular motions, as due to the interaction of the AGN radiation and the AGN wind with the material inside the torus. So this is a clear manifestation of self-regulation of the AGN fueling. Not all the gas in this compact is going to fuel the AGN. A significant fraction of the gas, we estimated like half of the gas, is going to be pushed by the AGN, by radiation pressure and the AGN wind, and is leaving the system. And this is, by the way, in agreement with the predictions of simulations of radiation-driven dusty molecular outflow in tori. They predict that due to radiation pressure, some of the material is going to leave the system. The outflow extends on larger scales outside the torus. In particular, the torus is not isolated, it's connected to the galaxy host to a network of gas lanes, and we identify in these gas lanes the distinct kinematic signature of gas which is leaving the system. In particular, gas seems to be located along the edges of the ionized wind Bacon structure. On larger scales, in the circumnuclear disk of NGC 1068, we see we identify where the most of the action for the molecular gas outflow is taking place. The molecular gas is being swept by the AGN wind at distances of 200 parsec, and this is because this particular geometry, the AGN wind is relatively wide angle, and the axis of the wind lies at a small angle relative to the disk of the galaxy, so it's able to produce this very efficiently. On larger spatial scales, up to a radius of 500 parsec, we see also evidence of outflowing structures. In particular, the radio emissions of this bow-shock arm morphology, and around this radio nebulosity, we detected high abundances of this particular species, C28 molecule, and this was interpreted in terms of UV illuminated molecular gas. So an imprint of the AGN feedback on the chemistry of molecular gas. We also see a discontinuity in the mass outflow rate radial profile, in the sense that we see that the outflow rate is around 1 solar mass per year on the scale of the torus, but is a factor of 60 larger in the circumnuclear disk. This is where most of the molecular outflow is taking place. In the bow-shock arm, we measure around like 6 solar masses per year. And this discontinuity of the outflow profile, we see several outflows on different time scales, on different spatial scales, suggests that the launch mechanisms can be different. We suspect that radiation pressure plays a key role on the scale of the torus, but probably at the AGN wind and the thermal pressure of the AGN produced by the AGN wind is responsible for launching the CND outflow, and the radio jet feedback is at work on larger spatial scales. Of course, if you want to stay clear from the unique object syndrome, you need to look at other AGNs, and this is the main purpose of the Galaxy Activity Torus and Outflow Survey, known by the acronym GATOS, where we use a volume-limited sample of 13 Cipher galaxies relatively nearby. They have been selected in ultra-hard X-rays from the Sweetback satellite. And for this first round of papers, we use new ALMA observations obtained in these two molecular lines, CO32 and ACO plus 423, which are sensitive to moderately dense, 10 to the 5, and very dense, 10 to the 7 molecules per cubic centimeter molecular gas. And of course, we are also interested in the dust continuum emission. And we did that by reaching this range of spatial resolutions from 7 to 10 parsec in this first round of papers. Do we see the tori in these AGNs? And what are the properties of this tori? In fact, we see CO line emission and continuum emission detected around the AGNs in our sources on scales or 50 parsecs. So we see the dusty molecular tori. In particular, continuing emission comes in two varieties. Unresolved point source emission that we attribute to synchrotron emission, probably the counterpart of coronal emission in the submillimeter, but most of the continuing emission comes from the extended disk-like components, the dusty tori. How large and how massive are these disks? A few tens of parsecs and masses of a few tens to the 5 solar masses. So these disks have properties similar to what we see in AG1068. In most cases, these tori are connected to the host galaxy, but they are kinematically and morphologically decoupled as they are perpendicular to the ionization cones. So they have this equatorial geometry. They don't know about the orientation of the disks, but they know about the orientation of the ionized winds we see in these differs. So this equatorial geometry is the expected geometry. This tori represents the launch sites of the molecular alphas we see further out. So AGN tori should be the launch sites of molecular outflows, and these molecular outflows might be the redistributing the gas inside the disk. So we have used ALMA and NOEMA archive data for 65 galaxies in this recent paper to reveal whether we see the imprint of AGN feedback on nuclear scales, in particular on the distribution of molecular gas. And in fact, we found a decreasing molecular gas concentration on these nuclear scales at for the higher AGN luminosity and higher Eddington ratio sources. The reason why we concentrated on nuclear scales is very basic. We want to look at nuclear scales because the outflows on these scales have time scales that are similar to the time scales related to the AGN duty cycle. So we were hoping to find a causal link between what the alphas might be doing to the distribution of molecular gas and the kinematics of molecular gas and the timescales associated with the AGN duty cycle. And in fact, we found evidence that AGN feedback is imprinted. How did we find this? Particularly, we use this prescription for the normalized distribution of molecular gas based on the ratio of gas surface densities measured at these two spatial scales, 50 parsec radius and 200 parsec radius. So with this concentration index, we are measuring what is the fraction of molecular gas, which has been assembled on scales of 200 parsec radii that remains in the inner 50 parsec radii. And what we see is this concentration index shows a turnover when we represent how this changes in our sample as a function of AGN luminosity. And the turnover luminosity is around 10 to the 41.5 Earths per second. So galaxies beyond this turnover luminosity show a significant decrease in the concentration of molecular gas. So there is a redistribution of molecular gas. And in fact, along this branch that we call AGN feedback branch, for the galaxies that show the most clear deficit of molecular gas, we see molecular outflow. So we see the agents responsible for clearing the material in the nuclear regions. Low luminosity objects lie along this moderately ascending branch, the AGA builder branch, and show higher concentration index. So in sum, we see evidence of two branches in this particular parameter space defined by the concentration of molecular gas versus the AGN luminosity. So they have the AGN builder branch and the AGN feedback branches. In fact, simulations identify a region in this parameter space defined by the column density, hydrogen column density towards the AGN and the Eddington ratio, where infrared polar outflows can be launched. And these infrared polar outflows are supposed to be launched due to radiation pressure. And in fact, AGN feedback targets, the ones that we see these nuclear scale molecular gas deficits, are located in the region where infrared polar outflows are expected to be launched. Of course, we are using James Webb data to know if there is a clear correspondence between what we see in ALMA and what we see in James Webb, but there seems to be a connection or a suggested connection between the AGN feedback on torus scales and on nuclear scales. So these are different scales, right? On nuclear scales, the scales we study with ALMA, we have proposed a scenario describing how the distribution of molecular gas may reflect the evolutionary stage of the galaxies that we analyze in this paper. We expect that gas-rich these galaxies should spend a sizable fraction of the lifetime moving along the AGN builder branch due to the action of large-scale bars, nuclear spirals, and this kind of perturbations draining that are able to drain the angular momentum, so increasing the concentration of molecular gas. Well, once you'd reach this threshold or this AGN luminosity, that seems to be a little bit magic at first sight, you start to be cleared. I mean, the gas it starts to be cleared by the AGN radiation and by the AGN wind. And in fact, this transition is quite abrupt. So the fact that molecular gas concentration changes very quickly, or very abruptly from the initial stage to the late stage of the AGN feedback phase suggests that this is happening on short time scales. And we have estimated these time scales based on the outflows we measure, the outflow rates, and the amount of the change in the concentration index. And in fact, we concluded that it's happening in a few tens of megayears. During this AGN feedback phase, where the gas is being pushed out, you expect that the AGN fueling is going to be interrupted for sure. So at the end of the AGN feedback branch, the gas reservoir, which is available for the AGN fueling, is the gas in the torus. So at some point, this is going to be the torus is going to be starving. So we are going to enter a black hole starvation phase or a AGN build down phase, whatever you may call it. And we have also estimated that this is very quick in the sense that the time scales associated with this phase are going to be short, a few tens of megayears, just based on the mass of the torus, of the tori we see in our sources, and assuming some accretion efficiency. So we expect that that galaxies are going to move in this parameter space to the left of the diagram until there is a new AGN fueling episode and the new cycle starts again. Of course, this is, well, you might say is a little bit qualitative, and we have to validate this scenario using numerical simulations that follow the nuclear scale concentration of molecular gas in a realistic AGN environment. And that's what we are trying to do. And this is a collaboration with the FIRE team using state-of-the-art zoomed-in cosmological simulations using different AGN feedback recipes. And in fact, well, this is a paper that's going to be submitted in a few weeks. So this is still work in progress. But the nice thing is that we see in simulations that they're able to reproduce the range of observed nuclear gas morphologies we see in real galaxies. And also, we are trying to date the fueling feedback phases by looking at how galaxies move in this parameter space defined by the concentration versus the excited luminosity. So we're trying to find what are the timescales associated with this changes of the concentration as a function of the phase that the galaxies are experiencing. Because we have seen that AGNs, the AGN feedback can be identified in the distribution, the kinematics of molecular gas. Do we see any evidence of AGN feedback on global star formation properties? This is tricky because we know AGNs are recurrent and transient events during galaxy lifetime. So we don't expect a strong correlation between the global star formation rate properties. The global star formation is happening on time scales of 1 or 2, a few gigayears in typical star forming galaxies, and the black hole accretion rate that we know is changing, and it has time scales associated of the order of a few tens of megayear. So we do not expect a one-to-one correspondence between these two. This is tricky. So observations and numerical simulations illustrate that only cumulative collection of AGN episodes that are encapsulated in the supermassive black hole mass can reflect the feedback on global star formation properties, characterized by the average or the global age of the stellar population or the quenching relevance when it comes to numerical simulation. And this is nicely illustrated by observations and simulations. It's a tricky business. So cumulative feedback is going to be reflected on global star formation properties. That does not imply that localized AGN feedback on star formation cannot be studied. In particular, especially result studies of currently active AGNs are required to understand and decipher localized imprint of AGN feedback. But this is because, having said that, as we have already mentioned when we discussed how we concentrated on nuclear scales, of course, the time scales of outflows are on the order of a few tens of megayear at most, and these outflows with these timescales are to be linked with traces of recent star formation, not global star formation, but traces of recent star formation that is happening on timescales similar to the timescales of the outflows that might induce some feedback on the ISM and so on the star formation properties. So we need traces of recent star formation like PAHs or traces of the young stellar population. Even if we do so, the results are tricky because sometimes the localization feedback can be positive and sometimes can be negative, depending on the object you see. And even if depending on a particular galaxy, different regions show different evidences of star formation feedback being triggered or quenched. And this is probably an indication that AGN power is not the only key variable, but only geometry is also important in the sense that how the AGN winds or jets or are distributed or what is the geometry relative to the ISM in the disk is a key ingredient. This determines to what extent the coupling is strong or weak. In this more recent paper, this is still work in progress. We are trying to see whether we see the evidence of agency effect on very small scales, on torus scales. In particular, we are using new ALMA observations in band 7 and band 8 to sample the emission of 3 molecular lines and the underlying continued emission, trying to dissect the molecular tori to spatially resolve molecular tori down to the inner 1.5 parsec radius region. And the goal here is to reveal whether the internal properties of the tori differ among the galaxies of our sample and try to link that or identify that as a signature of AGN feedback. And of course, see whether this is implying an evolutionary trend. Among the internal properties of the tori we are studying are the clumping structure, the contribution of diffuse versus dense gas, because we have different line ratios we can model, and also the properties of dust grains. Continued emission. So we have observations in two ALMA bands. So we have been able to obtain spatially resolved maps of the spectral submillimeter spectral index of dust continued emission. And what we see is a large variance of properties, right? We have a 6 galaxy sample, and we were lucky to see that not all the galaxies are the same, right? So that's already indicating that not all the tori behave the same. We see in one galaxy here clearly spectral index values similar to the expected galactic ISM values, or the other between 4 and 5. But we also see galaxies where these alpha values are relatively low, compatible with dust thermal emission, but between 2 and 3, which are pretty lowish. The radial gradients of the alpha values reinforce the idea that there are gradients, in particular for some galaxies. When you look at the inner regions close to the tori of these sources, we see relatively low values of the spectral index maps. Of course, there are other galaxies where the values are the expected one according to the Milky Way ISM values. How can we justify the presence of these low values. We have explored the possibility that the large grains can explain these low values. In particular, we have used uh, torus models using the approach of Gonzalez Martina and collaborators, and we have found that the presence of large dust grains as large as 10 micron can explain the low values of the low values of the spectral index that we see in some of these sources. So in these sources, we expect that these are heavily processed by AGN. Uh, uh, Small grains may have been preferentially destroyed, and the distribution of dust grain sizes could be biased towards large grains. And this is in fact in agreement with previous evidence based on reported low AV2NH values found in Seyfert galaxies by Biolino and collaborators. So you see the imprint of AGN feedback on torus scales on the properties of dust grains, in particular on the sizes of the dust grains. We have line ratios, and so we can play with these line ratios. We have CO to the 2, HCO plus for the 3, and C1, 1 to 0. They sample different physical densities, and in particular, these molecular line ratios both are inversely proportional to the dense gas fraction, but also there is chemistry that can play a role. In particular, C1 is very sensitive to XDR chemistry. So the thing is that when you look at these maps, especially resolved maps of the line ratios, you see a large variance. I mean, not all the galaxies are the same. You see a gradient also, very strong gradients in the line ratios. We have studied these two line ratios, independent line ratios, the C1 to CO and the CO3 to HCO plus line ratios. And in fact, we see two different behaviors. We see galaxies where the ratios are significantly high in the inner region. You see that in particular, the C1-CO ratio illustrated here is booming in the inner region. It's peaking at the torus. But in other galaxies, the same ratios are correspondingly lower. It's reach lower values. So these two galaxies, where we see the ratios are peaking at the torus, uh, can be understood in the framework of FTR models as indicating that there is a significant fraction of UV process diffuse gas. So we need diffuse gas to understand these ratios we see in some sources, while in other sources we do not need a high fraction of diffuse gas. Dense gas can fit all the ratios. So we see a large variance, right? Another property we wanted to understand on torus scales is the clump distribution. And here again, we were lucky to see significant differences between our admittedly small sample of six objects. We see in some sources low contrast in color density ratios. The way we study this is by deriving the color densities at two different spatial resolutions, 3 parsecs and 10 parsecs. So depending on the line ratio, on the ratio of color densities, well, you can figure out whether you have a very clumpy distribution of how highly packed are the clumps, or whether you need a component of diffuse gas. In some sources, there is a low contrast in the color density ratios, and it indicates that the clumps are highly packed, or the distribution of clumps is very uniform. So you're not very sensitive to the spatial resolution. So this is an indirect evidence that there is a dense gas component. So a signature of a weak torus scale AGN feedback. And these are the sources where you measure normal galactic ISM values for the spectral index maps, and also the same sources where you see that the XDR, PDR models we are using to account for the line ratios we measure do not need diffuse gas. It's just dense gas, right? In other sources that we identified as heavily processed, we see a high contrast in the color density ratio. You see here that is a high scatter when you try to understand how the column density ratio changes. So this is suggestive of an even highly scattered clump distribution and indirect evidence of less clumps superposed to a diffuse gas component. And we interpret that as a signature of a strong torus scale AGN feedback. And these are the sources where the gas, the line ratios indicate that there should be a diffuse gas component, and where the dust grain properties suggest that the AGN feedback is changing the properties of dust grains. So I think I have tried to illustrate to what extent ALMA have contributed to obtain a more complete view of the torus feature that is now seen as a multi-scale, multi-phase, multi-kinematic, dynamic environment. We see that tori are massive, larger than expected. This calls for a shift of the parcel-scale torus paradigm. Some of the tori dynamically perturbed, suggesting self-regulation of the fueling. They account for a sizable fraction of AGN obscuration, and they are perpendicular to the AGN winds and jets. That's the expected equatorial geometry. And I have also tried to illustrate that AGN feedback is revealed on torus scales due to these different internal properties of the tori as a function of AGN luminosity, and also on nuclear scales, where you see that the distribution and the kinematics of molecular gases changed on these nuclear scales for the most extreme AGN luminosity sources. So AGN science into the future. You already mentioned ALMA 2040. The white book of the ALMA 2040 group has identified two key scientific goals in this particular niche, which is the AGN science of the local universe. ALMA can probe the neutral molecular broadline region in the CO vibrational lines. This is a region where you expect that dust is sublimated, but molecules in this particular high column density and high volume density region can survive. This is the region between the ionized BLR and the torus. So this is the intermediate region where water masers are detected, and CO vibrational lines, vibrational excited lines could be detected by ALMA. Of course, you need very high spatial resolution, like 3 or to 5 milliards, similar to the ELT. Of course, by increasing the spatial resolution to this level, you can also probe the emission of rotational lines, CO, HC, and HO plus, with very high spatial resolution, and you can spatially resolve the tori in a large number of objects. We have started to do that in a small number of objects, but of course, into the future, ALMA could do that in a much larger sample of objects. Also, ALMA would be able to probe AGN feeding and feedback cycle in quasars that are more cosmologically relevant. Even if they are nearby, they are more cosmologically relevant because they are more similar to the most extreme objects we see at high redshift. And of course, we want to know what happens beyond the typical AGN luminosities we are probing within the Gata survey. We want to know what happens in the quasars, right? But you need high spatial resolution. We have started to do that. We have a program in ALMA, but that for a small number of objects. And of course, we wanted to increase the number of quasars that we are able to observe. But we will need a factor of 3 longer ALMA baselines, a factor of 5 high sensitivity compared to current ALMA to do that in a larger sample. ALMA will be a key in the facility in the AGN science in the local universe. Other facilities also can be instrumental in serving the purposes of several scientific goals. And this is just a list, a personal list, probably biased, of things that we need to study. We need to obtain high resolution data of molecular and ionized gas and dust in circumnuclear disk regions. We need to quantify the fueling processes down to Dora scales of the different instabilities we have identified. We have started to identify in local Seyfert galaxies, but on a much larger sample. We need to compare with the predictions of zoom-in simulations. This is starting, but this is still uncharted territory at some point. We need to resolve the multi-phase and multi-scale structure of tori and the outflows launched from them. And we need to understand the roles of different driving mechanisms, accretion disks, radiation pressure, and jets. We need to study the relevance of jet wind power and the orientation, so geometry and the coupling efficiency. Of course, we need to study localized and cumulative impact of engine feedback on star formation, structure, and kinematics of the ISN. So it's important to study physical localized impact for sure, but it's also important to study cumulative impact of AGN events, both in AGN and also in inactive galaxies. So this is something that I had to do. With that, I think I will stop here and I will ready to take questions.
Fantastic. Santiago, thank you very much for a very all-encompassing talk on everything ALMA. I know I have questions. There's lots of applause. There's an explosion of applause. But yes, if anyone would like to ask questions, we're going to try asking questions this time. In the React button, there is a raise hand option. If you'd like to ask a question, please raise your hand, and then we can call on you to unmute, and we can talk digital, virtual, face-to-face. While people are potentially phrasing their questions, so Santi, one of my questions is the dependence on coupling you touched on, and so for like the feedback loop that you showed this build up phase, and then you showed the outflow phase, and so that was basically looking at the amount of expelled material versus X-ray luminosity. Could this be a function of coupling as well? Where you're having strong coupling situations that are producing a lot more feedback into the host disk, and then you're getting a boost in the softer X-ray emission as it's interacting with the hosts. What are your thoughts on that?
Yeah, I think, but there are two important parameters, which is, of course, the AGN power. More powerful AGNs are, in principle, able to produce more damage or produce more feedback. But the way the AGN wind is oriented, so the geometry in particular, is a key. And if you look at the molecular gas concentration ingots versus AGN luminosity, you see these two branches, but there is a scatter, right? So for a fixed AGN luminosity, you have a scatter. And I think the scatter is not statistical. Is that because it's reflecting that for a fixed AGN luminosity, depending whether the AGN is oriented, you can do a big damage or not a big damage. It is true that people using simulations, for example, jet-driven feedback, they see that the feedback is produced not only along the jet axis, but also in this perpendicular direction, because they are able to inflate hot cocoons of hot gas that are able also to produce some damage in the lateral direction. But there are different actors, but of course the geometry is very important. So I think the scatter in this relation is telling you that the geometry plays a role, right? But we need to consider geometry is tricky. You need high spatial resolution and models and comparison with simulations to really understand what is the influence of geometry, not only the AGN power.
Fantastic. Vivian has her hand up first. We can go to her.
Great, thank you. Santiago, thank you for a really nice talk. I really enjoyed it. I think you answered a lot of my questions about how luminosity, aging luminosity, the geometry, the ISM patchiness, how all of that tied together, right? And so my question is perhaps, and I apologize if I missed this, how does the feeding of it, how does AGN duty cycle kind of play in all of this? As another timescale question that I always ask myself about this. And since I think you have the power of the data set to say something about the fueling, and I was just wondering whether or not that's something we might be able to solve with either this data set or data sets in the near future, to kind of start tying in the AGN duty cycle kind of into the timescale question.
Thank you. This is a very interesting question. We are trying to do that, but in fact, Francois Combs is part of the team, and one of the plans is to derive the gravity torque maps on different spatial scales and try to relay the fueling on different spatial scales with the feedback we see in different scales. Try to see where is the fueling happening on what scale and what is the feedback happening and on what scale to see whether there is a balance at some point. But this is something we have to do, right? But it's not yet done. But I agree with you that the quality of the observations allow for this kind of studies because we have all the ingredients. We know how to derive the gravity torques and the fueling efficiency, but this is something we have to do.
Thank you. Thank you.
The next question comes from Suvas. Suvas, are you available? Can you unmute?
Can you hear me?
Yep.
Okay. Yeah, like I have a question. So basically, in the context of X-ray analysis of this, so like you saw that there's some volume limited samples. So the number of X-ray detected, these obscured agents are very less, right?
Obscure, I mean, do you mean how many obscure genes we have in our sample? Sorry, I didn't get exactly what you want to
I
ask.
mean, in the general descriptions, when we study like such agents, so you showed a plot where the column density with the Eddington ratio.
Yeah.
So, can you go to that plot?
Yes.
It's easy to phrase that question.
Oops, sorry. This is, I'm sorry, I was too, okay, this one, I guess.
Yeah, correct. So, like here, in the X-ray analysis, we classify them as a Compton thick and Compton thin agents, right?
Yeah.
And basically, like lot of their lower energy radiation is getting absorbed, and they are re-radiated in the X-ray. However, the sampling here you showed basically with the swift bat, right? And in the swift bat, actually, the in the higher energy part, we will not be able to constrain the column densities. So for that, we need a lower energy like X-ray, that's like the XMM or Chandra.
I have to say that these column densities we are showing in this diagram, right, are derived from ALMA, not from X-rays.
Okay.
That's different. So we in the first paper, this 2021 paper, we showed that there is a correlation between the column densities we derive from ALMA and from X-rays, but they do not quite agree. There is a correlation. There's some scatter. So, but as you know, I mean, the X-ray derived column densities are not necessarily the same as the column densities we derive with ALMA. First, because the X-ray column densities might correspond to very small scales, and the column densities we derive with ALMA are average within our beam, which is nice, but it's not parcel scale rate yet, right? So they are average on scales that are different, but we see a correlation. It says that the molecular tori are contributing to the obscuration, right? I mean, it's not the same value, but they are contributing significantly to the obscuration. But some of our sources are content thick. There are clear cases like NGC there's 7582, 1068, or these are content thick based on X-ray observations. And even with the, as you see, in the case of 1068, the column densities we derive from ALMA are really high, right?
Yeah, that was my question. Like they seem pretty high values, like 10 to power 24.5. Those values are very high for X-ray.
That's right. And I have to say that for these values in this paper, we assumed uh, Milky Way alpha CO conversion factors. That's debatable. Of course, as you derive the condensities from CO, some of the sources have CO1 to 0, CO2 to 1, CO2 to 2. So that depends on the line ratio you assume. And we were really very conservative in the sense that we assume the same values as 1068 we are using CO3 to 2. But probably that is underestimating the condensities. Right? That probably will help to make an agreement both X-ray and ALMA column densities.
Yeah, and another question, like term you mentioned, torus host connection.
Sorry, say it again.
Uh,
I have some problem with the
torus
sound.
host connection.
If there is what? Sorry.
You use a term torus host connection. Okay, I'm typing if in case you are missing.
Sorry, I cannot hear you very well here.
Sebas, actually, why don't you toss that into chat, and then
Yeah,
we can then
yeah.
let Stephanie go with the Taurus host connection. So, Stephanie, why don't you ask your question, and then we can bounce back to that.
Sorry about that.
Hi,
Yeah, so
Santiago. Thanks for your talk. Can you hear me?
Yes.
Okay. Yeah, this is very exciting. I look forward to seeing your paper. I also wanted to ask, I think it's similar to Vivian's question with the duty cycle, but I really like this figure with the build-up and the feedback. So I guess I had kind of a small two-part question, but one of them is the fact that the non-AGN seem to be at the lower concentration.
Yes.
So are you interpreting this to mean that the gas buildup is the fueling of the AGN? Like the AGN is the effect rather than the cause? And I guess that's kind of related to the duty cycle question, but if you
Yeah,
want
I
to.
mean, yeah, well, I can use this plot as we are in this slide. The non-AGN are located here, which are relatively, uh, not the highest concentration, but
Mhm.
they seem to be if you prolong the AGN buildup, they allow at the end of the AGN buildup. So at some point, you would say that they are starting the cycle again, right? But they are still very low luminosity AGN. Probably it is
Mhm.
not the AGN, it's these X-ray binaries or something that it contributed to the X-ray luminosity. There's no AGN at all, but they seem to be located in this parameter space as a continuation of the AGNB Lagrange.
Mhm.
So there seems to be a sequence, right? So, but I agree with you. One of the pieces that we are missing here is the fueling, right?
Mhm.
And this is something we have to do. This is up on our to-do list.
Okay, and my second part on that same kind of picture in that diagram, I think this may be also missing. I'm not sure of your full sample here, but do you have major mergers here? Because I'm thinking major merger might completely change the parameter space in some other way, so that.
No, our sources are, well, maybe I didn't insist on that, are disk isolated galaxies, right?
Okay,
Not galaxies are not 100% isolated, but they are not mergers, right?
right. Okay. Thank you. This is very interesting stuff. Thank you so much.
Thank you.
All right. There are no more hands right now. But Santiago, I think for everyone here, really appreciated this presentation. Thank you again so much. And it was really insightful.
Thank
So,
you.
I want to see if I can share one more screen before we all head out. Folks, I just want to remind you, then if you want to stay involved, please remember to give us your input on questions that we can be preparing for the decadal survey. Also, if you or someone you know is defending sometime in the or recently or in the near future, please share this interest form with them for the dissertation jamboree that we're looking to put together in either late April or early May. And then finally, our next meeting for AGN, all things AGN SIG related, is our AGN coffee discussion group. So again, there's a Discord sign up for the QR code here. I believe that's what that is. And then we'll also see you again later next month for the Spotlight Series talks where we're having Dominica Kroll and Justin Kader talking about their work. So thank you very much, everybody, for coming. We really appreciate having you, and we hope to see you again next time. So take care, everybody. Thank you.
Thank you. Bye.